Dynamic programming. It's the base idea for a lot of algorithms and also for a lot of problems on competitive programming. And it's shocking to know that despite being so crucial, most of the reference material about dynamic programming only describes what is in that thing and some examples of problems, but not how to deal with new problems. I am here to fix that. First and foremost, I'm going to assume that you already have some knowledge about what dynamic programming is and just a few examples about that, but you are struggling to be able to solve new problems. I'm going to leave a link on the description below and also a video over there in case you need an introduction to dynamic programming. Now let's start with the good stuff. The states are the cornerstone of dynamic programming, and learning to recognize them is key to solving those problems. The notion of state is so general that it can apply to other kinds of algorithms as well, not just dynamic programming. But what is a state? Many optimization problems can be summarized as taking a sequence of choices, with each choice being a trade-off between two different things. A restriction for future choices and optionally a cost or a profit. Intuitively, a state is determined by the set of restrictions imposed by the previous choices. So, depending on which choices are taken, the restrictions change and that determines the state. And what we want is to maximize the profit of any given state or minimize the penalization. Another way of describing what states are is the set of all relevant information after taking some of the choices. So the choices change the environment, and the information about the environment is what constitutes a state. Let's illustrate that with the problem more simple I can think about that. Consider a grid of R rows, and these are the rows, and C columns. Each cell in the grid has certain amount of apples. You start here at the upper left, and you can only move either right or down, and you want to collect the maximum amount of apples. For example, path like this one, it could be a possible path, or another path like this one would be valid as well, but something like this wouldn't be valid because that would require to go to the left, and there are only these two allowed movements. Maybe many of you already know this problem because this is a very classic problem, but I want you to follow me just to check what is this notion of the state that I am talking about. Suppose that at some point you are here. Then, as I previously stated, you think of the choices is usually a trade-off between profit and restrictions. If you move in this direction, the profit would be this apple, and the restriction would be that you will not be able to get any of all the apples in the future. If you move down, then the profit would be 1 again, and the restriction would be forget about all of it. In this case, the state would be determined by how many columns we already renounced to and how many rows we already renounced. So in this case over here, if we are here, that would mean that we already renounced to these 3 columns over here and these 2 rows over here. So we could say that the state here is number of rows 2 and number of columns 3. That is an order pair of 2 and 3. And from here, if we move in this direction, then we would be changing to the state 2, 4, and a movement like this would change to the state 3, 3. And now notice that even when we talked about the restriction that we already imposed about the current solution, the other way of thinking in the state as the information about the environment that is the current position, that also works and it's exactly the same as if the rows were numbered starting with 0 and the columns also numbered starting with 0. If you think about restrictions or the variables of the environment, both of them are the same and you can even combine both if that makes it easier for you to think in the solution of the given problem. Something that may be helpful when solving dynamic programming problems is to draw a tree or a graph to illustrate how it's possible to move from one state to the other. For example, here we are at the state RC, a very generic state, row R, column C, or we renounce already R rows and C columns. And we can do 2 things here. One is to move right and the other is to move down. We can only do those 2 things. Moving right, it would increase the current column or renounce to a column. It would be R and C plus 1. And the other would be to renounce a row or going down. That would mean to pass from RC to R plus 1C. And after having a tree like this drawn, then it's time to think about how the profit would change. If we know the maximum amount of apples we can get from here and the maximum amount of apples we can get from here, then how we could know what the maximum amount of apples that we could get from here. So we have 2 choices, either move right or move down. The answer would be the maximum of the 2 choices. Do you follow me? Just taking the maximum of those 2 would not be enough. Why not, you may be thinking? So this may be a little bit tricky to see if we move so far away from the original problem. What would happen if we start in a place that already has dots? For example, if we are here the maximum that we would get from here would be the maximum from here and the maximum from here, but there is another dot here, so we need to add that dot into the equation. After putting that information in an equation that is basically how the states relate with each other, we have this over here. If you remember, for recursion we also need a base case. We cannot just use a single recursion like this forever. Let's add our base case here. Here, this is the base case, and what it means is that if we already renounce to all the rows, then we cannot get any more apples. Or if we already renounce to all the columns, that means that we cannot get more apples from there. Another way to see that is that if we go outside of the grid, we cannot continue. This may seem weird because the original problem doesn't state that you can go outside of the grid. But going outside of the grid doesn't get anything worth it to do that, and it simplifies the equation because the optimum would be always to get over to here, and this allows us to not having to put the boundary check on the equation. Here is an implementation in C++ of that solution. I used memorization because I don't want to deal for now with the details of the order of filling the table. I think the order of filling the table should be very straightforward. However, now I want to focus more on the idea about getting the states. I hope after this you already have some intuition about what are the states and why it's important to find them, and also that it's possible to think of states either as all the relevant information of the environment or the set of restrictions previously imposed by the previous choices. And this way of thinking, it makes sense once you have enough practice. So we are back where we started, just Git Good without actually telling you how to Git Good. Of course not, because having the goal to assimilate this concept will really help. And also, we are not done. I only showed you what kind of intuition we want to grasp, but in order to grasp that kind of intuition, it's necessary to have it grounded in more precise concept, and also to tie this new concept with previously assimilated theory. Let's talk about the search space and how the states are developed from there. Let's go back to the previous problem. And let's imagine that you don't know dynamic programming, so now you are considering to solve it using a brute force algorithm. Each possible path on the grid would be a sequence of R minus 1 plus C minus 1 steps. Let me show you how that happens. Here, for example, there are 7 rows and 8 columns. So if we take something like this, I'm just being arbitrary. The number of times it went down, it was r minus 1 because it has to go down. The number of rows minus 1 to move from this row to this row, it has to move right c minus 1 times, because to move from the column 1 to the column c, it needs to move c minus 1 times. This thing over there can be represented by a string. It would be with this string over here. As you can see, there is 6 times the D character, that means going down, and 7 times the R character, that is going right. So a brute force algorithm could be thought as generating all the strings of R and D's with exactly 6 minus 1 R's and R minus 1 D's. There are a lot of possible strings for that. Just keep in mind that for each string with this number of R's and this number of C's, there is one path over here. Now let's call each path a solution for this problem. For a grid of 25 times 25, there would be 50 factorial divided by 25 factorial squared solutions, and that's a lot. It's around 1.26 times 10 to the power of 14. This may seem like dynamic programming is a totally different technique from recursive search, something completely unrelated, but that's not true. Let's consider this other example. This is a smaller grid because I want you to show you the entire search space. The search space is the set of all possible solutions, and in this case it's the set of all strings composed of 3 R's and 3 D's. It's really the set of all paths, but we can think on them as strings because it will be easier to illustrate them as strings. If we generate all the strings using a recursion, the recursion will travel to this tree of recursive calls. Let's see what happens here. Here at the beginning, it will generate both cases. One string started with D, or a path going down, and the other one going right. When it goes right, it goes over here again, down and right, and down and right, and here it goes down because it already went 3 times right. So for each one of these nodes on the lowest level, so these leaves, so over here, it corresponds to a string. Or as I said before, for each leaf on these lower levels, it corresponds to a single solution, and that can be represented with a string that it would mean either going right or going down. For this problem in particular, one solution is a path and also can be represented with a string, but generally speaking, a solution is a sequence of choices. Let's introduce the other concept. The concept of a sub-solution. The sub-solution is a prefix of a solution. This may seem a little bit far-fetched, but if we check again on this tree of recursive calls, each node over here corresponds to a sub-solution because each path to reach each one of the nodes corresponds to a prefix of many different solutions at the bottom here. So the path from one solution to the root, it's basically all the sub-solutions of that one. But something that would be present in every recursion would be not just in the path that it follows, it would also keep the profit or the accumulated profit in this case. That would mean the number of apples collected along the way. In this path over here, that would mean going down and then right, that is here, it would collect 5, so there should be a 5 over here. Let's fill all the nodes over there and see what happened with those values. Now I assigned all of those values to and the nodes of the tree. These values correspond to the number of apples collected on each sub-solution, or how many apples were collected along the way for each path in the recursion. And let me remind you why we are doing all of this. We are aiming to abstract from this in a natural way the concept of states on dynamic programming. I want to show you how this tree over here is related to the state space in the dynamic programming, and hopefully extrapolating that relationship, it would be easier to do the same transition from brute force to dynamic programming on other problems. So let's continue with this. I want you to notice that there are many branches that look remarkably similar. This branch over here, it's exactly the same of this branch, of the other branch over here. And these two branches, even when they are not exactly the same, they have some things in common. Have the same structure, and the difference between the value at the root and the value of each one of these different nodes is the same. This thing is repeated over here. This same pattern is here and it's here as well. So aside of just checking parent, we should do a connection between this thing that we see on the tree and what is happening right here on the tree. If we check where we find this kind of pattern, for this one that is over here, it's going down, down, right, right. So it would be down, down, right. And here, this other one over here that is similar is down, right, and it's down, right. It ends up here again. For this other, right, down, and it's write down, and it ends here again. It looks all of these similar branches are similar because they end in the same place here. Our intent now is to classify all of these sub-solutions in some buckets that correspond to branches that are similar to each other. But we need some way of defining when a branch is similar to another, because you can see here the values of that are on the nodes of each branch is not always the same even when the branch is structurally similar. Now, to expose how these sub-solutions are related each other, I marked with blue the optimal paths from one branch to the lead with highest profit. So if you are in a particular branch, just follow the blue path and that would be the optimum from there. There are two ways of getting 15 apples, and because of that there are two blue ways marked from the root. But aside from that, if we already have the tree, the algorithm for getting to the optimal solution would be only start on the root and follow the blue path. Like here, this is one possible, and the other possible is this one over here. I marked this in blue because I wanted to expose these similar branches. These two big branches, for example, are structurally the same, even if they have different values because they arrive with different number of apples, but everything inside of them it behaves the same. So the blue paths are exactly the same. We can say that this branch over here and this branch over here are equivalent, or this branch is equivalent to this branch, that is, this branch is equivalent to this branch, and it's equivalent to this other branch, and to this other branch, to this other as well. And if you pay attention again, these other two branches are equivalent. Let's introduce the definition of equivalent subsolution. This is the definition that we will be using for two subsolutions that are equivalent. The idea of two subsolutions being equivalent is that they have a branch that behaves the same. Right now we are only caring about the optimum solution that starts of each branch. These two branches are equivalent because they have the same path from the root of the branch to the maximum value of a leaf. So it's right, down, and right, down. The rest of the branches structurally the same, but on the definition that we are using, we don't really care about the rest of the branch. It may seem weird to not care about the rest of the branch and just care about the optimum, but after all, we are aiming to find the optimum. In other problems, there may be branches that we can prove in advance that there are suboptimal. It can be better if we can just ignore those suboptimal choices and consider the branches equivalent. And also, I think it's easier to remember that two sub-solutions are equivalent if we can be sure that their optimal choices are always the same. This definition is good enough for what we are aiming to do. So now we said that we want to separate all the sub-solutions on buckets, and each bucket would be a state. Now let's consider three sub-solutions that we are naming them A, B, and C. Every sub-solution is equivalent to itself. Just remember what means for a solution to be equivalent. This should be pretty obvious. Then if A is equivalent with B, then B is equivalent with A. If the optimum choice from A is the same that the optimum choice from B, then it should be the same in the other way as well. This third one is a little bit more interesting, and this is the transitivity property. If A equivalent with B and B equivalent with C, then A is equivalent with C. Just remember what means to be equivalent, and you should be able to see that this third property holds as well. The important part is that these three properties together are an equivalent relation. The equivalence relation is another topic. You can research about it for yourself, but for our purpose, it gives you license to split the sub-solutions in different buckets, such that two sub-solutions would be equivalent if and only if they are in the same bucket. So instead of considering all the sub-solutions separately, we could just consider the buckets, and we will call those buckets states. What is a state now? And a state is a set of sub-solutions such that all the sub-solutions on that set are equivalent each other. And now the state space is a partition of the set of all sub-solutions in state. So in this tree, we could represent the state of all these branches like this one by just the position on the grid. It would be the position 2, 2 because it's zero-based index. The number 1, 1 is a way to represent an state, but it's not the state itself. I say this, and I remark this, that this is important because I want you to have this clear. Dynamic programming is still considered all possible solutions, but dynamic programming separates the sub-solutions in these buckets named states in order to save resources and save time. Okay, you may be thinking all of this is well and good, but isn't this lecture just a bunch of abstract stuff with no value in practice? And to that, I respond that my goal is to make easier for you to start solving dynamic programming. And for that, I firmly believe that a solid understanding can smooth your way. So I will leave you a list of hints to put in practice all of this theory. this is the list of tips that I want you to focus in order to link all of this theory to something more practical. Think which variable would you use if you were going to solve the problem by brute force. Then consider to represent the state as a tuple with the values of those variables. Then ask yourself, could you compute the value of one of those variables with the values of the others? If that's the case, you could remove them from the state. For example, if you are dealing with a problem of having a liquid of a fixed volume in two containers, if you already know the amount of liquid that is in one of the containers, you could know the amount of liquid that is on the other. So you could factor out that information. If there is a solution that cannot be fully represented by the values of those variables, if that's the case, you should reconsider your approach. The variables that are used to classify the states are variables that are meant to identify all the important information of each subsolution. If there are some information there that cannot be abstracted or deduced from your set of variables, then your set of variables is incomplete. Then ask yourself if it is possible that two not equivalent solutions have those variables with the same value. That would mean two different solutions belonging to the same state. If that's the case, also reconsider your approach. And then once you know the states to use, consider to draw a diagram, because drawing a diagram, at least at the beginning, it makes easier to find the recurrence, just in the way we did it over here. You should be able to apply these tips right away and start solving dynamic programming problems. But on the next video of this series, we'll tackle some examples using this mindset developed over here. Maybe that will clarify misunderstandings on this video. As always, I hope this video is useful for you.